Okay, here in Finney, page 33, number 5, the big F, it says graph the curve. What are the initial and terminal points, if any? Indicate the direction which the curve is traced. Okay, this one will not have any initial or terminal points because, as you can see, t has been allowed to go from negative infinity to positive infinity. And so, therefore, we're going to get the entire curve. As you've seen on the other one, we didn't get the entire curve because we started t at 0. Therefore, we were getting a portion of the curve starting at a certain initial point and continuing on, possibly to infinity, and we wouldn't get a terminal point there. So in this case, we're not going to get a initial or a terminal point, so we're going to have to look at both some negative t's and some positive t's in order to get the full idea of what this curve is. All right, then it says B, find a Cartesian equation for a curve that contains the parameterized curve. So again, we're going to solve for t, we're going to plug it into the other one. Okay, so what portion of the graph of the Cartesian equation is traced by the parameterized curve? So there we go, we're going to have to figure it out. All right, so we have x equals 3t and y equals 9t squared. For x equals 3t, that's the easiest one to solve for t. Let's do that. X equals 3t. Dividing both sides by 3, t is equal to 1/3 x. Let's plug that value of t into the y equals equation. So now we're going to have y equals 9 times 1/3 x, and we're going to square that. Simplifying, that's 9 times 1/9, 1/3 squared and x squared. 9 times 1/9, x squared. 9s are going to cancel. And we have y equals x squared. So we have the parabola y equals x squared. Since t is allowed to go from negative infinity to positive infinity, we're going to get all the values that we know about, and we'll get the full parabola instead of just a piece of it. We're quickly making a simple chart. I'm going to start t, I'm just going to start t at -3. This won't be all the points, but we could get more. -3, -2, -1, 0, 1, 2, and 3. And then we have x and y. When we plug in -3 for x, we're going to get -9. When we plug -3 in for t, for y, -3 squared is 9. 9 times 9 is 81. And that makes sense because -9 squared is 81. Awesome. -2 plugged in gives us -6 here. Let's go ahead and plug in the rest of the values just for x. It'll be nice and quick. That's going to give us -3, 0, 3, 6, and 9. And then for y, when we plug in -2, that's -2 squared, or 4 times 9 is 36. Makes sense because -6 squared is 36. Plugging in -3, I'm sorry, -1. -1 squared is 1. 1 times 9 is 9. Plugging in 0, we get 0. And then, of course, 3, 6, and 9 are going to yield the same values because we're squaring. So we'll get 9, we'll get 36, and we'll get 81. And if we plot these points, we get both sides of the parabola. Awesome. Let's move on and take a look at another problem. All right. Finney, page 33, the big F, number 9. Same set of instructions here. Graph the curve, initial and terminal points. And here we will get initial and terminal points. This tells us that t goes from 0 up to pi, not including pi here, and therefore indicate the direction in which the curve is traced. Find a Cartesian equation for a curve that contains the parameterized curve. By the way, on that last problem, the direction in which the curve is traced, it starts and moves from top left down, going to bottom right until it hits the vertex, at which point it changes direction and then moves from bottom left to top right, as it is the parabola opening up. Okay, remember, think of parameterized curves as a particle moving along a path. That's the best way to think of this. All right, so x equals cosine t, y equals sine t. Here's our bag of tricks. We're going to pull out the Pythagorean identities because we know that cosine squared, t plus sine squared t is equal to 1. From the unit circle, and of course this is written slightly backwards. Normally we see this as sine squared t plus cosine squared t equals 1, but order doesn't matter in addition. And cosine squared. How do we get cosine squared? Well, that is x squared. So we're going to square both sides of this equation. And x squared is equal to cosine squared. Similarly, we're going to square both sides of this equation, and y squared is equal to sine squared. With a simple substitution for cosine squared and sine squared, we have the curve x squared plus y squared equals 1. And this is the circle with center at 0, 0 and a radius of 1. This is the unit circle. So, moving on from that, it says that we need to find the initial and terminal point. So again, make a table. We're going to put t here and x here and y here. So, when t is 0, x is, cosine of 0 is 1. Y is, sine of 0 is 0. So, our initial point is 1 comma 0. 1 comma 0 is over 1 up 0. So we are starting on the positive x-axis. And then the question is, are we going clockwise or counterclockwise? So, this is our initial point. And then choosing some nice values of t. I'm just going to choose pi over 4. I'm going to choose pi over 2, 3 pi over 4. And finally, I'm going to choose pi, but according to this, we are not actually getting to pi. So that's what we're getting close to, but there'll be a hole in the graph. We won't quite make it there, which means we don't actually have a terminal point. If this was less than or equal to, then this value of pi would give us a terminal point. In fact, what I'll call it is a terminal hole. Trying to be funny. Of course, you know, I'm Honig's, so I am funny. All right. So let's call it the terminal hole. Terminal hole in the graph, right? So plugging in pi over 4, these are square roots of 2 over 2. The question is, where are we moving? Well, square root 2 over 2 comma square root 2 over 2 is in the first quadrant. So we've moved from the x-axis up to the first quadrant. We are going in the counter clockwise direction. All right, plugging in pi over 2 into cosine is 0. And pi over 2 into sine is 1. So we're now on the y-axis. As you can tell, we've moved from the x-axis into the first quadrant up to the y-axis, 0, 1. When we plug in 3 pi over 4, cosine is negative, and sine is positive. Plugging in pi, cosine is negative 1, and sine is 0. And that's the portion of the circle that we get. Okay, so we get the top half of the circle, almost with a hole on the left-hand side. And as you can tell, there's our direction. All right, let's move to another problem. Similar to the problem we worked out of Larson, where they were working backwards on this one. Find the parameterization of the curve, that is the line segment with endpoints -1, -3, and 4, 1. So on the last one, they gave us the xy equation. Here they're giving us 2 endpoints to a segment. We can go ahead and find the xy equation. okay, from this. This is just 2 points. We need to find slope. We need to plug it into y minus y1 equals m times x minus x1. So, again, remembering the two equations that we had before, that x is going to equal x sub 1 plus delta x times t, and y is equal to y sub 1 plus delta y times t. Delta x and delta y are going to come from the slope. Slope's going to come right out of these 2 points. Let's figure out the slope. So we're going to take 1 minus negative 3 over 4 minus negative 1. And our slope is 4 over 5. And so we will use delta x is 5, delta y is 4. Let's make sure we kind of say that this is delta y over delta x. Now again, we could use anything here for delta y and delta x that matches with the slope, so we could have used 8 over 10. Delta y could have been 8, while delta x is 10. Let's go for the simplest here. So then we need to have, well, we need the slope, and then we need point. Well, which point? It actually doesn't matter. We can use either one of the points. I'm going to use the one that's positive, and we're going to form these two equations. So y minus y1 equals m times x minus x1. It's not actually needed. We just really need the slope. And now we have it. Because it's the slope out of that equation is what we really needed. Okay, and they've given us 2 points. If we use the other one, we get a different parameterization. So let's write these. X is equal to x sub 1 is 4 plus 5t. And y is 1 plus 4t. And we have a parameterization. Here's our two equations, x and y in terms of t. Okay, so parametric equations is actually a lead-in to vectors, because these will be the x and y's in terms of t would be the x component, the y component of vectors. So stay tuned for notes on vectors, notes on polar equations, and problems work for both polar equations and vectors. Okay, I hope that this helped. Thank you, BC students.